if you were at the two previous talks, you already saw what I'm interested in. So there's a fancy word called categorification. And in fact, this word first appeared in a lecture room in my presence. I was in 1998, I was in Princeton in the institute, and just a first-year postdoc, and there was another first-year postdoc who was, and we were expected to give 15-minute presentations about our activities, and we all were dressed informally, and he was the only one in formal suit, tall and handsome. So he said, "Michael is my name, categorification is my game." And you can imagine who this was, because this was Michael Havanov, and like Havanov cohomology. And indeed, he kind of invented the word, or at least was the most active guy spreading the word. Although categorification as an idea, so the idea to replace less categorical objects by more categorical objects, in fact, has been in mathematics for a long time. So raw idea of categorification so the idea is not mathematical, it's meta-mathematical. So whenever you have some construction where vector spaces are involved, you should replace your vector spaces by some categories. And here, of course, you have a choice depending on the situation you are in. So these categories can be abelian, additive, or triangulated. And recently, actually, and I'm a big fan of the new world of DG categories, differential graded categories. So now, well, vector spaces are objects on which some algebraic structures act, and algebraic structures themselves are some kind of algebras or rings or even groups. So like this plus this equals the representation theory, right? So an algebra acts on the vector space. That's the basic setting of representation theory. So, well, an algebra is a vector space with multiplication. So then, one level up from algebras, we have monoidal categories. So monoidal structure is a tensor product defined on a category. So again, depending on your education and the specifics of the problem, they could be abelian, additive, triangulated, DG categories, whatever. As I said, representation theory starts when we have an algebra acting on something. So a module is replaced by C, a monoidal category. And let's say M, just a category. And then a monoidal action. So yesterday we actually saw an example of such situation. So there are famous categorifications, and so two famous examples of categorification. Just to mention, so don't worry if you haven't met them. So first is so usual and categorified. In the usual world, we have H of the affine Hecke algebra. And in the categorified world, we have the derived category of coherent sheaves on standard variety equivalent to diagonal action of G with convolution. So again, I'm not trying to define anything. I'm just putting letters on black box so that you would see notation, and if you meet it again, you would recognize it. Or if you know parts of the story, that you would know that it's in the story. And the second example is U dot, which is the direct sum of U dot lambda mu is the Lustig quantum group. And in the categorified world, there is this U dot underlined the Havanov Lauda Rukia categorification. So again, these are algebras, these are categories. Yeah, I mean you can do it like this, or you can just say that it's sum over mu mu. I mean it's the version of the quantum group which is without unit, which has idempotence instead of units. So again, I'm not talking about this. I'm just saying that recent developments in representation theory really fit this scheme. Let me mention what is so what do we get? Or maybe there's one remark. To return to the world of vector spaces. Well, we have a so from categories to vector spaces. There's a method which is called growth in the group. So take the growth in the group. And now there are three versions of this. In the case, so let me call this case 1, this case 2, and this case 3. So in the first case, it's the usual growth in the group. So if we have a short exact sequence of objects in an abelian category A, then we consider a group which is generated by classes of isomorphism of objects. Well, I guess you saw this before. And the relation that if we have a short exact sequence, then the class Y equals the class Z plus the class X. So it's the relation. And then growth in the group of A is, the free abelian group generated by these classes, quotient by relation star. in the second case, for additive categories, we don't have short exact sequences, but we have the notion of split Grothendieck group. And in the third case, for triangulated category, we still have the notion of Grothendieck group. So for a triangulated category, let's say D, the Grothendieck group of D is given by, well, as before, so free abelian group generated by classes of isomorphisms, quotient by relation double star, where double star says that if we have an exact triangle, then the class of Y is the class of X plus the class of Z. Okay, I just want to mention this. So well, this is an abelian group by definition. If you wish, you take the complexified Grothendieck group. So you tensor by, say, complex numbers. Then given a category, and as an outcome, you get a vector space. If your monoidal structure is good enough, then given a monoidal category, as an outcome, you get an associative algebra. So, so we know how to pass from the categorified side to the usual side. So what do we get from this? So it's second remark. So what do we get from categorification? And the answer is canonical basis in vector spaces. So let me comment this. So when you have just a vector space, all bases are the same. If you have more structure on a vector space, well, you can talk about orthogonal bases or orthonormal bases, but still there are so many such bases. Now, when we have a category, we have much more choice of properties of object. For example, if we're talking about abelian category, we can talk about projective objects, indecomposable projective objects, or irreducible objects, or injective objects. And then their classes land in the Grothendieck group and become special elements. And very often such special elements give rise to quite exceptional bases in Grothendieck groups. And if your monoidal structure behaves well, this basis is multiplied in a very special way. So indeed, a very interesting combinatorics, non-trivial combinatorics appears from this. So what is known as Kazhdan-Lustig basis for the Hecke algebra, or for the affine Hecke algebra, or Lustig basis for U dot, come this way. So the corresponding categories have, well, maybe irreducibles, as in the case of Lustig basis, or projectives, as in Kazhdan-Lustig realization in coherent terms. And then you get a very special basis with special combinatorial properties in the corresponding decategorified picture in algebras, modules, and so on. Okay, so let me stop here, because this is not what I wanted to talk about. This is just the usual generic blah, 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 which says that going one categorical level up and then down produces interesting combinatorics, which is extremely important and like has been investigated for a long time. And as I mentioned in this canonical basis picture, the idea implicitly was in mathematics since mid-80s, even though Khovanov invented his word categorification in mid-90s. So kind of the importance to consider categories with special classes of objects was clear for Lustig and other people doing geometric representation theory. Now, another reason to go categorical is that somehow as objects grow, the structure becomes more and more hidden. Let me illustrate this by hierarchy of, well, small and then bigger and bigger objects. So, so size hierarchy. So let's start from vector spaces. So finite dimensional vector spaces. So what is bigger? Well, you'll say infinite dimensional vector spaces, but there are very, very many of them. And I choose to say, well, one word is Tate vector spaces. But I don't want to give a definition. Instead, I give a typical example. A typical example is vector space of formal Laurent series in a variable t. So if you think about this vector space, it's unions, so inductive limit of projective limits of finite dimensional vector spaces. So to go one level up or down in this hierarchy, you consider, well, first all projective limits and then all inductive limits. But we'll be dealing with this concrete vector space. It's good enough. So next level is two Tate vector spaces. Well, in a way, that's another iteration of the same procedure. So you take first projective limits of Tate vector spaces, then unions of such. But here is a typical candidate. It's just Laurent series in two variables. So first you add one variable, then you add another variable, and then you consider this as a vector space over the base field. So kind of this is just, you know, functions. So like functions on a finite set, functions depending on one variable, functions depend on two variables, and it's reasonable to think that functions in two variables is a bigger vector space than functions in one variable. Informally, formally we'll see what the difference is. Okay, so now another type of hierarchy. So given a group G and a abelian group, there is group cohomology. I don't want to give a definition, but here somehow I'll get H1 of G with coefficients in A. Here I'll get H2 of G with coefficients in A. Here I'll get H3 of G with coefficients in A. So in fact, I can put here dot, 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 and also here I can put dot, dot, dot. And in a way, the message of this whole considerations is that somehow, well, the horizontal lines indeed give correspondence. So for finite dimensional vector space, first cohomology naturally appears. For Tate vector spaces, second cohomology naturally appears, and for two Tate vector spaces, third cohomology naturally appears. Well, another incarnation of this hierarchy is, well, I'll explain the words, but it's an element of a group. And on level 2, we'll have what is called a torsor. So actually, the main part of my talk will be explanation of such words. And then in here, I'll have what is called a gerb. Well, also, to continue, maybe one more line. A finite dimensional vector space has what? It has dimension, which is an element in Z. Also, it has determinant. That's just the top exterior power of V. And what is it? Well, it's a one-dimensional vector space. And when we pass to level 1 or level 2, right, so one level down, we don't have dimension. But we have dimension like this of which is something, and we have determinant of such vector space. It cannot be a number, it's infinite dimensional, right? But it is something which I will describe, and this is part of what I'm doing in this talk. Also, we have determinant of this vector space, and it cannot be top exterior power, because there's no top exterior power. It's an infinite dimensional vector space. It's something. And believe me, further, we have, on next level, we also have something, something, something. So why am I interested in this? I'm interested in this, so I'll explain some construction. So I'm doing representation theory. And representation theory is about representations of some groups. And a typical group we deal with is, so typical to consider. Well, related to each of these. Well, what can be more natural given a vector space than consider its endomorphisms, GLN. Well, this will be, so V finite dimensional. Yeah. So we can continue considering automorphisms. So on the next level, we'll have GL of this huge vector space. And then on the next level, we have GL of this even bigger vector space. So what do we know about them? So this group has a distinguished function called determinant. This group, as I'll explain in 10 minutes, has a distinguished central extension called the canonical central extension. And so huge part of representation theory of Kac-Moody algebras and Kac-Moody groups is related to this central extension. What we'll see is that this group, and that's why it is like much bigger than the previous one, has a distinguished 3 cocycle. So it has a categorical central extension, a generalized central extension. Now, the message, even before all constructions, is that, well, central extensions are naturally seen by usual representation theory. You can extend the group and then consider representations of the extended group. Or you can consider projective representations in the old terms. Now, when you have 3 cocycle, no representation theory in vector spaces feels this 3 cocycle. You cannot say that this is a representation of the extended group. However, if we make this group act on some category, there's a way to see this 3 cocycle. So in the remaining part of this talk, I'll give an elementary and totally discrete, so no algebraic geometry involved, construction of this central extension and this categorified central extension. So this is the material of my talk. In particular, these ... words will be explained. So, so let's start. So this is called words in the hierarchy. So we fix A, which later will be the multiplicative group of a field. So it's a commutative group, abelian group. And G, which later will be one of these, so just any group, any discrete group. So start from the bottom or top part of the hierarchy. So we start from, well, we know what element A in A is. And on the next level, we have the notion of a torsor over a point. So this is just a fancy word. So by definition, it's a set T with action of the group A. And this action is simple and transitive. Well, apart torsors, we have trivial torsors. It's just A itself, T node, which is A, with the multiplication giving the action. Now, trivialization of a torsor. That's just identification of the torsor with the trivial one. It's phi, an isomorphism from T node to T. Now, it's clear that to define such isomorphism, we just need to put to say where the element 1 goes. So such phi is just one element T in the torsor. So like phi T of A is A times T. So what else? I'll need one more construction. This is the construction of tensor product of torsors. So suppose we have two torsors, T1 and T2. Then T1 tensor T2 is the quotient of the direct product of sets by equivalence relation, where T1 comma A T2 is equivalent to A T1 T2. So it's a very natural construction. You can check that it's again a torsor. Very good. So we can form a category of torsors. A tors with this tensor product. So it's a groupoid. So all maps are isomorphisms. And even a Picard groupoid. I don't want to write this down, but Picard groupoid is just a groupoid with tensor product which is invertible. So every object is invertible. You can now, if this scared you, let me notice that there are some natural examples. Namely, if A is just V, some vector space with addition, then an A torsor is the same as an affine space W over V. So what is an affine space? It's a space of points to each of which you can apply a vector. Now, vectors sit in V, points sit in W. Then there's an operation applying a vector to a point and get another point. Now, another example, so if A is K star, which will be our basic example, then A torsors is the same as one-dimensional vector spaces. Indeed, given a torsor over K, or maybe it's better to go in the other direction. Let L be a line. It's a one-dimensional vector space. Right? Then the corresponding torsor, TL, is just L without 0. So you throw away 0, and then, of course, a multiplicative group starts to act simply transitively, so we get a torsor. And I'm not writing this down, but tensor product of one-dimensional vector spaces corresponds to tensor product of torsors. Of course, you'll say that there's only one-dimensional vector space. This is true or not true. There's only one class of isomorphism of one-dimensional vector spaces. But there are unbelievably many of them. There's not even a set of them. There's a class of them. So, and then final example for those who likes differential geometry. So for one particular vector space, A being H node X omega 1, so for the space of one forms, so with addition, there's one particular torsor which is called con. That's this space. Oh, maybe, maybe I'll add a vector bundle. So suppose we have some X with a vector bundle E. Then global sections of one forms with coefficients in endomorphisms, that's a vector space. And connections forms an affine space. And so a torsor over A. This is just in case you don't like category theory, but somehow like differential geometry. Okay, so I described what a torsor is, and by now I think we are used to them. Now, so for G, a discrete group, then torsor T and an A torsor or T G over G. It's just a collection T G G in G of torsors, of A torsors for all A in A. And now definition. Tg is multiplicative if, well, we are given isomorphisms Tg1 tensor Tg2. These are torsors. I am taking their tensor product. 2Tg1, G2. And this is the product in the group. So they are called phi G1, G2. You can imagine what conditions they satisfy. Now, a remark is that a multiplicative torsor is the same as central extension. So, so suppose we have a central extension of G with the help of A. Right? So suppose we have a central extension. Then, well, so this map is pi. Then G to pi inverse of G is a multiplicative A torsor on G. So, well, preimage of 1 is just A. Now, preimage of 1 acts on preimage of any element. And this is the structure of the torsor. So we have I leave as an exercise to check that this is a multiplicative torsor. So, anyways, we get classification, namely central extensions, which is the same as. Huh?
Think of G hat himself as a group space of an A torsor.
Yeah, but you know everything is discrete, so I'm not talking about total space. And in fact, I define the torsor only over a point. Yes. Yes. So then this is in a way a lemma, which says that multiplicative A torsors on G are, well, classes of isomorphism of them, are in bijection with central extensions which are given by second cohomology of G with coefficients in A. Okay, and one final thing in this torsor story is the following. So suppose that T is an A torsor, then suppose we have also a G action. G acts on T. So G times T to T. Then we get a distinguished function phi from G to A. How does it go? So, well, given an element in G, I should get an element in A. Well, this is so to get such function is no, I'm wrong. There are many functions like this. Given T in T, we get a function. So we need to fix an element in the torsor. We need to trivialize the torsor. So it's very easy to write this function. So I'll call it phi t. So phi t of G is the following. I take T and compare it to G of T. Right? Since the action is simple and transitive, there is only one element A which takes T to G of T. So put this function to be equal to A. Okay, so we have everything I need from torsors on the blackboard. Now one level up. So we're categorifying everything. So another definition. Gerb. An A gerb. Over a point. Is a category gamma such that all arrows are invertible, so it's a groupoid. It's connected, so all objects are connected at least by one arrow. And for any objects, gamma 1, gamma 2, the space of morphisms from gamma 1 to gamma 2 is an A torsor. And the composition is isomorphism of torsors. well, take this as a definition. We'll see an example of gerb a bit later. But then we repeat the whole bunch of constructions. So there's a functor between gerbs. So it's a category. So map is a functor between gerbs. Then I need tensor product of gerbs. And it's given as follows. So let gamma 1 and gamma 2 be A gerbs. Then objects of gamma 1 tensor gamma 2 are just objects of gamma 1 times objects of gamma 2. So I'm only interested in morphisms. Then gamma 1 tensor gamma 2. So the space of morphisms from one such pair of objects, which I denote by gamma 1, gamma 2, to another one, which I denote by delta 1, delta 2, is simply, by definition, tensor product of gamma 1, delta 1, tensor gamma 2, delta 2. So you see, kind of, to define tensor product of more categorical gadget, I'm using tensor product of less categorical gadget. Okay, so I have the notion of tensor product. Then I can say what is gerb and A gerb over a group G. That's very easy. So for every G in G, we have a gerb gamma G, and that's it. And definition, this gerb gamma is multiplicative if we are given, well, as before, only in capital letters, phi G1, G2 from gamma G1 tensor gamma G2 to gamma G1, G2. And finally, the lemma says that multiplicative gerbs on a group G, multiplicative A gerbs on the group G are in bijection, well, again, classes of equivalence of them, in bijection which now with now H3 GA. You see that we are going deeper and deeper along this hierarchy. Yeah. Equivalence. So here equivalence, here isomorphism. Wait, no, this is equivalence of gerbs. It's a functor which is an equivalence. There are no isomorphisms in this question. Yeah. Well, and one final thing to mention about gerbs is that suppose a group G acts by functors f G from a given gerb to a given gerb. Then a choice of object gamma in the gerb provides multiplicative a torsor on G, so a central extension. So let me tell you what it is. So what do I need to define a torsor? To every element G in G, I need to put in correspondence TG, an A torsor. And what is it? It's just the space of homes from G of gamma to gamma. If you haven't forgot my construction for distinguished function, you see that I went one level up, and instead of distinguished function, I obtained a distinguished torsor, and it's a multiplicative torsor on the group. So one level down, we had G acting on some torsor and a function phi from G to A. This is almost the end of categorical nonsense I need. I'll just mention the words for the next level. I mean, this hierarchy goes on and on and on, depending on how categorified you are, what is the size of categorical diagrams you can consume. But one further level will start from the notion of a two-gerb. Let me call it D, and an action of a group G on D. So any G gives rise to a two-functor FG D D. So what is a two-gerb? It's a two-category where the space of one morphisms from any object to another object is a gerb. So it's a hierarchy starting from functions, then go torsors, then go gerbs, then go two gerbs. So at every step we apply the same categorification thing. The previous level becomes the space of homes at the next level. Okay, so that's all I wanted to say in general. Now let's talk about Tate and two Tate vector spaces. And to this end, I'll work only with this vector space, which is my V, and double, so two variable Laurent series. So let's take this. So definition, a lattice in V is a one-dimensional K of T submodule L such that if we invert T, so L of T inverse is isomorphic to the whole thing. Well, it's very simple. So standard lattice that's just L node, which is K of T itself. Now the set of all lattices is called Sato-Grassmannian of so lattices are called, so this set is called the Sato-Grassmannian of this vector space. Well, given two lattices, so every lattice is an infinite dimensional vector space over the base field. So we cannot talk about its dimension. But we can talk about the relative dimension. Dim L1, L2 is defined as follows. So we have L1, L2, and their intersection. L1 intersects in L2. So every embedding here is finite dimensional. Huh? Oh, well, rank 1. Rank 1. So every codimension here is finite. So this is dimension of L2 mod L1 intersect with L2 minus dimension of L1 intersect with L2. So somehow we subtract the common infinite dimensional piece, and then we can compare dimensions. If everything were finite dimensional, this would be indeed relative dimension. And there's a notion of a relative determinant. So that of L1, L2, that's very simple. So we take the top exterior power of this vector space and divide, so tensor by inverse, by top exterior power of L1 intersect with L2. So it's a one-dimensional vector space, so a torsor.
Or only pairs subtract the portions of finite dimension. That's a condition.
Every two lattices are like that. Every two lattices are like that. So very good. I defined relative dim and relative det. Now, what is absolute dim and absolute det? Here are the definitions. So a dimension theory on Sato-Grassmannian of this vector space. D is a function which associates to a lattice a number. So it's a function but what is the condition? The condition is that, so such that d of L2 is d of L1 plus the real relative dimension of L1, L2. So this is a number which is God-given. This is our choice, and this is our next choice. So you see that the only thing we really need to define such dimension theory is its value on one lattice. So, so dim of this vector space is just the set of all dimension theories. What is it? It's a Z-torsor. If you have some dimension theory and you add the same number to all values, you get another dimension theory. Now, there's another thing which is called determinant theory. So this is our definition. Determinant theory. On the same Sato-Grassmannian. It's again a function which takes L to, well, let me call it delta of L. Delta, which takes L to delta of L, and this is a K-star torsor, or maybe a one-dimensional vector space. With the condition that for any L1, L2. Delta of L2 is isomorphic to delta of L1 tensor as one-dimensional vector space. The actual det, which is defined over there, of L1, L2. So what is all determinant theories? So this is all determinant theories. On Sato-Grassmannian. And well, what is it? It's a K-star gerb. So if you add the same torsor to all values, you'll get again a dimension theory, a determinant theory. Sorry. So now the functoriality of the picture. If the group, so take GL of this vector space. It acts on, well, I'm not specifying how I'm defining this, because, of course, any automorphism I am considering should preserve the notion of a lattice. And this is the condition. So it's called, I think, Jacobian matrices or something like this. So in algebraic terms, this means that your matrix can be, so in the standard basics of monomials, your matrix is allowed to be infinite, but there's finitely many diagonals.
It can't be thought in terms of equivalent points on the group scheme here?
I think not. So it acts on Sato-Grassmannian of this vector space.
It has to preserve one lattice.
The notion of lattice. So a lattice should go to another lattice. So for any element of. So then it acts on all gadgets we define. So it acts on dim of K of T and on det, which was a gerb, if you remember, K of T. And the yoga I was advertising says that whenever a group acts on a gerb, you get a central extension. So fixing a lattice, so fixing a determinant theory, For example, let's put delta node of the standard lattice to be equal to K star, right? So this is fixing a determinant theory. As I said, to define a determinant theory, you have to pick a lattice and tell the value on the lattice. The rest is given by conditions. We get a central extension. It does, but all of them are isomorphic. So this is the standard Kac-Moody type central extension of this GL infinity. So this group is called GL infinity. It has a very famous central extension, and here it is. Now, in the remaining 0 minutes, let me say what I do next. You can imagine the ideology, but not the realization, and categorical level will be 1 up, as you can imagine. So given this double Laurent series, one defines the set of 2 lattices which I call 2-Sato Grassmannian, and the notion of 2-dim. So before dim was a Z torsor, now 2-dim will be a Z gerb, and 2-det. So det was a K star gerb, so this will be a K star 2 gerb. And so then GL of this huge thing acts on this 2-det. So it acts on 2-Sata and on 2-det. And then by the general yoga, one gets a multiplicative gerb on GL of this double run series and a 3K cycle. Phi in, well, H3 GL. So kind of a higher central extension. Now people have been doing representations of, you know, S, L, N tensor C of T, T inverse, S, S inverse, for example, or the corresponding groups. So double loop groups. In the usual non-categorified world, and it's quite a prosperous activity, but so the shadows of these 3K cycles are not seen because we are dealing with usual representations. So this is the kind of invitation. One needs to develop categorical representation theory of this group or these Lie algebras, such groups, so double loop groups, to see this canonical cycle. So people know very well that the critical level for Katz-Moody is extremely important. It's canonical and very important. And representation theory without this critical level just doesn't exist. So when we consider double loop or double Katz-Moody, double affine Lie algebras or groups, the critical level lives in the third cohomology. And one needs representation theory which can see this critical level. And this cannot be in vector spaces. It has to be categorical because vector spaces they feel central extension but not third cohomology class. Okay, so let me stop now. So all this, by the way, is our 2010 paper with Kobi Kremnitzer from Oxford. So Kobi Kremnitzer from Oxford. So the story is like this. Michael Kapranov was advertising this idea of double Tate spaces, iterated Tate spaces, shared this idea with us and with Denis Osipov in Moscow, a student of Parshin. And there are two papers with basically the same material.
Lining up in Broderick's theory in dimension 2?
So,
Broderick's theory in dimension 2?
So people want to make this 2-Sato and corresponding to affine Grassmannian an algebraic object, but somehow the whole activity was to avoid algebraic geometry because it's tempting, but it's too big to be approached by finite dimensional schemes so far. So this categorical blah 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 is exactly invented not to. I mean, if you know this activity about usual Sata Grassmannian, usually there are no categories. Usually there's an infinite dimensional variety or an int scheme and a determinant line bundle there and whatever. So this gerb I'm constructing is the incarnation of this determinant line bundle, and so on. So, and we know that the usual Kac-Moody central extension comes from the failure of determinant line bundle to be equivariant. And that's exactly what happens here.
This is the representation theory of GL K over
No. This is still one bracket. That's the double bracket. So I want to study something like representation theory of this or something like this.
Right. So, what are other groups of this sort that?
Huh?
What are other groups of this sort that
So-
representation theorists care about? What are other objects?
See, it is for this reason that I asked.
Uh-huh.
Are you thinking of GLKT as loop groups in some sense?
Well, you can embed a loop group into this.
So therefore, the coefficients could be instead of GL could be an arbitrary simple group, right? G, you can think of. Does it make sense to have that?
Yes, you can do that, and corresponding class may or may not exist. So it's this delooping machine. So this is the incarnation of first Chern class. That is the incarnation of second Chern class. For some groups, there's no first Chern class.
The characteristic class has to weigh itself off in that sense.
No, these are some characteristic classes, but they are realized kind of not geometrically but categorically.
And so the object that you probe the representation theory with is again Sartor-Grassmannian, or what do you use if you have a different group?
If I have, so first of all, this picture is in a way universal.
Yeah.
So you can embed any loop group into this infinite matrices. Yeah. And in the same way, there are Grassmannians for all groups. They embed as orbits in this one. I mean, that's how you basically do it. I can say it in a couple of words. So if you have some group G and its representation V, if it is good enough, I consider V of T. I consider GL of this, right? Now, if the G is a representation, then G of